Assalamu alaikum wa rahmatullahi wa barakatuh. This is the fifth part of Mechanical Oscillations, Chapter 4. At the end of this video, you are going to be able to define driven oscillations. Remember first that we have mentioned that free mechanical oscillations can be damped or undamped. In free undamped mechanical oscillations, the amplitude and the mechanical energy are constants, and the characteristics of the undamped mechanical oscillation are proper period, proper frequency, and constant amplitude. Now, what is free damped oscillation? An oscillator, like the pendulum, is said to be damped when it oscillates with a decreasing amplitude with time. The mechanical energy of the damped oscillator decreases due to the existence of a friction, a resistance, etc. What are the characteristics of this motion? First, it has pseudo period T, where T is greater than the proper period T0. When the damping is low, the friction force causes a decrease in the amplitude. With each return trip, the motion is not called just periodic. We call it then pseudo-periodic. The value of the pseudo-period is constant. Pseudo-frequency F. F equals to 1 over T, so it is less than the proper frequency F0. Pseudo-angular frequency omega, so omega equals to 2 pi over T, then it is less than the proper angular frequency omega 0. The amplitude. Actually, the amplitude of oscillations decreases with time and eventually becomes 0 when the block stops. There are different types of damped oscillations. Before, let's remember the free undamped mechanical oscillation, where it has a proper period T0, proper angular frequency omega 0, and the amplitude is constant. The first type is slightly damping. In this case, the period is approximately equal to T0, where omega also is approximately equals to omega 0. We say that the amplitude decreases gradually with time. The second type is large damping. In this case, the period is approximately greater than the proper period. The pseudo-angular frequency is approximately less than omega 0, and the amplitude here decreases with time and eventually becomes 0. The critical damping. In this case, there is no more oscillations, and we say it is non-periodic. The amplitude in this case dies. After defining these forms of damping oscillations, it's good to know some information. Do you remember the question we have asked in the first video? It is the time to answer it. Do you have any idea? In cars, there are shock absorbers that turn it into a damped harmonic oscillator and keep it from continuing to bounce up and down after every bump or pothole a tire encounters. This makes riders feel more comfortable, of course. Now, of what type of damping should the oscillations of a car's shock absorber be? Is it slightly damping, large damping, or extremely large damping, which is critical? Good. It is the last one, which is the critical damping. Let's solve this application. The adjacent document represents the variation of abscissa X of center of mass G of a solid connected to a horizontal elastic pendulum. The solid starts at t0 equals to 0 seconds from the equilibrium position with an initial speed v0. Take the horizontal plane passing through G as the reference level of the gravitational potential energy. Specify the type of oscillations made by the pendulum. Pause the video and think of the answer. Good. The amplitude xm of oscillations decreases with time. Then the oscillations are free damped. Now, referring to the document, determine the value of the period of motion and then name this period. Check this figure. The first three oscillations are made during 4.1 seconds. So, we say the period is this time over 3. So 4.1 over 3 equals to 1.367 seconds. The name of this period is pseudo period. The last idea, driven oscillations. The system is considered driven when it is provided by amounts of energy just enough to compensate the loss in order to oscillate with constant amplitude. The oscillations are not free because there is an external intervention. The clock pendulum without the electric battery performs free damped oscillations because the resistance of the air and the friction with its axis of rotation. For this reason, the engine battery system is used to maintain the oscillations to compensate for the loss of energy dissipated. The system then is called exciter. Driven oscillations then are periodic, and they have a period equal to the proper period of the pendulum. Let's solve this application and end with this lesson. The adjacent document represents the variation of the abscissa x of center of mass G of a solid of mass m equals to 100 grams, connected to a horizontal elastic pendulum. The solid starts at t0 equals to 0 seconds from the equilibrium position with an initial speed v0 equals to 0.3 meters per second. Take the horizontal plane passing through G as the reference level of the gravitational potential energy and the pseudo period as 1.37 seconds. The first part. Knowing that the kinetic energy at the moment t equals to 2 periods is 2.74 millijoules, determine the average power of the force required to drive the oscillations between 0 and 2 periods. Remember the expression of the average power, which is the absolute value of the variation in the mechanical energy with respect to variation in time. You should find the mechanical energy. And the mechanical energy at t equals to 0 is the kinetic energy plus the elastic potential energy. But at equilibrium, the elastic potential energy is 0. So the kinetic energy at 0 seconds is half mv squared, which is 0.0045 joules. Now the average power is the absolute of the difference between the mechanical energy at the second period minus the mechanical energy at 0 seconds over delta t. Now, the mechanical energy at the second period is given as 2.74 times 10 exponent minus 3 in joules minus 0.0045 joules that we have just found divided by 2 times the period, which is 1.37. And the answer is 0.64 times 10 exponent minus 3 watt. To end up with the lesson, it's good to remember the whole areas that we have mentioned in this lesson. Mechanical oscillations can be free, driven, or forced. Free mechanical oscillations can be damped or undamped. An oscillation is characterized by its period, frequency, and amplitude. The nature of motion of undamped oscillator is simple harmonic when its mechanical energy is constant and amplitude is constant. The differential equation of a simple harmonic motion is x double prime plus k over mx equals to 0. The time equation is x equals xm sine or cosine omega 0 t plus phi, where the proper angular frequency omega 0 equals to the radical k over m, and the proper period t0 equals to 2 pi radical m over k. Moreover, we said that during undamped free oscillations, the mechanical energy is constant, where the kinetic and potential energies are constantly transferring to each other. The period of energies is equal to half that of oscillations. During free damped oscillation, friction forces cause mechanical energy to dissipate by thermal transfer. The pseudo-periodic oscillation are characterized by pseudo-period t, which is greater than t0, pseudo-frequency f less than f0, and amplitude that decreases with time. During driven oscillations, the amplitude remains constant due to an external energy input. This is the end of part 5 of chapter 4. Thanks for watching.